Okay, welcome to the Tutte Colloquia. Today we're very happy to have Jim Luetke, who is a professor in the Department of Industrial and Systems Engineering at the University of Wisconsin-Madison. Jim works on optimization and its applications, and today will tell us about data-driven sample average approximation for stochastic optimization with covariate information. Jim.
Okay. Thank you, everybody. And I appreciate this chance to share my work remotely. I would rather see you in person, but I'm glad to still have this chance. And start off by saying that the majority of the work that I'm presenting today is in collaboration with primarily my postdoc, Rohit Kannan at UW-Madison, and also with Gujan from Ohio State. So let's just start off by kind of motivating the problem, the setup here. So this notion of data-driven optimization using covariate information. And I'm going to kind of take it a step back all the way to just considering, the basic problem here is the general setting of optimizing with some uncertainty in some of the parameters. Okay, so for throughout this talk, I'm going to use Z as the decision. Use X. We'll see. I need X for something else. But Z is going to be like the vector of decisions, representing the things we want to decide. The script Z is a feasible region. We'll assume that's known. But somehow in the cost function, which could be something fairly complicated, I'll give you an example in a minute, it depends on some uncertain parameters. Okay, so I'm going to denote that by this vector capital Y. And so as written up here, this problem not really well specified because I told you Y is uncertain. So what value should I put into this to solve this problem doesn't make sense. So we have to sort of add some level of modeling assumption to make this into a well-specified problem. And there's a couple main approaches to doing that. And so the first one is going to be the one I'll be focusing on in this talk is sort of the stochastic optimization approach, where you would generally assume you have some for example, that expected cost. In stochastic optimization, you could also do things like a different risk measure or something. Or alternatively, you could talk about robust optimization, just to kind of put this, different ways of thinking about the problem out there, where distribution of Y, you to support one of the possible values of Y that you could possibly see, and then rather than averaging over that, you take a worst case analysis where you sort of minimize what would be the worst possible outcome you could see, cost of that, and that certainly can have some advantages in terms of modeling. I'm going to not focus on that approach in the talk today because I'll be interested in settings where that might be overly conservative and maybe might be thinking about making decisions repeatedly over time, so that you don't want to necessarily be so conservative. You really want to, have a decision framework that hopefully does well on average instead of just preventing against the worst case. So we're going to focus on this stochastic setting, and to make that a little more concrete, I want to give you an example, actual sort of model, and this will also be sort of the setup of the model I'll use in a kind of a case study, computational study at the end. So we'll have that kind of out of the way as well. And so this is a two-stage stochastic optimization model, where it's kind of a resource allocation model. So in the first stage, before I observe any uncertain outcomes, you can think of the uncertain outcomes in this case are going to be demands of different customers. So that's the capital YJ. But before I observe the customer demands, I'm going to make some decisions about some resources that I'm going to sort of have available to meet those demands. So you could think of that as being maybe a staffing problem where the resources are different employees who have different skill sets, perhaps, or it could be even just having some level of materials that you produced. Okay, but having these resources available costs you money. So part of the objective function is the cost of allocating those resources or making them available. So that's the first part of the cost there. And then what's going to happen is I make that decision, I fix those resource levels, and then I'm going to, after that's fixed, then I'm going to assume I observe the customer demand. So I observe that vector capital Y, and now I get a particular observation of little y. And then once I've made that observation, now I'm going to try to use those available resources in the best way possible in order to meet all the customer demands, and do so at maybe minimizing the penalty of unmet demand. So in this model in particular, this WJ variable is some amount of unmet demand, and I'm going to minimize some penalties from not meeting the demands. And then, I have these limitations on the VIJ is how much of resource I allocate to customer J, so I can't allocate more than I have set aside at the beginning, the ZIs. And then, I ideally would do this allocation in such a way that I meet the customer demand. So I would like this the B's times the B's to be at least J. If that's not possible, then this WJ variable will have to go up as much as needed to account for the unmet demand, which then is recorded in the objective. Okay, so that's just to kind of put this two-stage stochastic optimization sort of notion, give us an example of that as we think about these optimization under uncertainty problems, make that a little more concrete. But I'm going to step back now to this kind of this notion of the general stochastic optimization model, and start thinking about, in particular, where does this distribution come from? So that's one of the main potential limiting assumptions of the stochastic optimization paradigm. Is we assume we know the distribution of the random factors, right? So we have this expected cost minimization that's happening here, but that's a limitation. So one thing that you could do, which has been observed for a while, is if you have access to samples of this random variable y, so let's call those yi for one, then you can kind of build a data-driven approximation where instead of minimizing the expected value, because you can't do that, you don't know the real distribution of y, you minimize this sort of sample average, right? So I replace the expected value with this average over the cost over all the different observations yi. Okay, so I could think of that as in this resource allocation model, I could say, well, I have observed how much demand I've had for the last, say, 100 days, and you just think of those as a possible outcome, a joint outcome for all the different customers. And then I try to say, okay, well, let me make a decision that's going to minimize the average cost over all those outcomes. So that's sort of the data-driven approach. In that case, there's a nice theory that supports this. So this is known as sample average approximation. First of all, you can show under fairly reasonable assumptions that the solutions do converge to the optimal solution as if you knew the true value. And you can even sort of bound kind of the convergence rate. So you can sort of say the error is on the order of 1 over the square root of the number of data points that you have, which is not a great convergence rate. But given that this is you think of this as like Monte Carlo sampling, it's kind of the best you could expect to have. Okay, so that's sort of a bit of context of sort of the traditional stochastic programming approach and how you use data. But now we want to add a twist to this, and this idea is the idea that when you're making a decision, just using past observations of your demand might not be such a good idea, because you might have additional information. So I'm going to use that additional information. I'm going to use the word covariate for that, where if over the past 100 days, in addition to knowing the demand, I knew additional things about what was happening that day that I could maybe use to predict the demands better, then of course I would want to make use of that, right? So that's that's kind of this whole machine learning is very good at that. That's become very popular, and there's a lot of people studying, how could we better predict something given some sort of independent variables or covariates. And so in this setting, we're imagining that instead of just having past samples of the observed parameters of interest, or the demands in this case, we also have these covariates going with it. Okay, so you would imagine that you would try to use now when you're going to make a decision today, you imagine you have a new covariate. Okay, so this is the observation that this value X that you would then use to predict what's going to happen today before making this decision. Now, of course, that prediction is still going to have error, right? So even though you hope that this helps you predict better what's going to happen today, you also should recognize that there should be error in this. And so the question is how can you integrate, what's a good method for integrating this learning, and in particular factoring in that, the learning still has error within the optimization model. Okay, so that's the key question. And maybe just to, give this another sort of, flavor or an application, you could think of this being useful, for example, in power grid, say power generator scheduling. There's a problem known as the unit commitment problem. That's an important problem there. And so there you certainly are making decisions with uncertainty. So for example, how much renewable output you might have, or what's going to be the loads in various customer locations. So that would be like that uncertain parameter vector capital Y. But definitely you also have, at the time you're making this decision, you have other information, right? You're not blind to making this. You have information that you could try to use to predict what will be the outputs of renewables, or what will be the demand. For example, of course, the time of day, the time of year, and maybe you have certain current weather observations that would be part of the prediction of the weather for the future. So just an example to kind of make it a little more concrete that you would have this covariate information. And so, the first thing you would do, this is kind of a traditional approach, and people have been doing this for a long time, is just sort of separate these things, right? So okay, I want to predict something, so we have all these fancy machine learning models that can help us do this prediction. So, given my data, let me do a prediction. Okay, so that's the first step you would do, is I would do a prediction. It could, train a prediction model. Given my data xi and yi, maybe I have some model class f, and I want to have, f of xi to be the prediction of a point yi. And for example, maybe I minimize, the sum of the losses over the data set, that's the empirical loss. And maybe I have some kind of regularization on the function class f that helps, with out of sample performance there. But, just an example. It doesn't really matter, but generally you sort of offline, you do this prediction based on your data. And then what you would do is, you given a new covariate x, I'm ready to make my decision for the day. I'll just, I have this model, I'll call it f hat, that came out of step 1. And so I just plug in x into f hat. I take that as my prediction of what my vector y is going to be for the day. And I solve this now deterministic optimization model. Okay, so that's a very reasonable thing to do. And you would certainly expect it to work well if your prediction is very accurate, right? So if somehow, given x, this f hat of x was very close to what the y is going to be, this would be perfect, right? This is exactly what you'd want to do. But the challenge is it's not always going to be perfect. So there's limitations to these predictions. So when it's not correct, you might be misled. You might not make a good decision when you have errors. And that's kind of the classic sort of stochastic programming motivation. And so one thing though that I will mention as an advantage of this approach is it's very modular, right? So these two steps are completely separate. So, anytime, people are doing great research on developing new machine learning models, if you can do better predictions in step 1, you do it. And then all you have to do is, plug in different f hat in step 2, right? So that's sort of a nice thing about this approach. So in fact, actually, I think, maybe I just want to pause for 1 second and give people an opportunity if they wanted to interrupt with a question. This is kind of setting up the main framework before I start talking about different approaches, how you might do that.
Sorry, I had a question. Can you give an example of what the covariate would be for the stochastic model that you mentioned earlier, the two-stage stochastic one?
Yeah, so there's resource allocation model. So in that setting, it's, the thing we're predicting is customer demands. And so, it's just this is a simple version where it's just a static model. So it's like for the day, I'm going to have some amount of customers show up and I want to be able to serve them. And so, then it's just a matter of, what information might you have at the beginning of a day or at the point when you have to make the resource allocation that could help you predict customer demands. And so that could be things like, it depends on, what is the service or the product that you're selling, but maybe the weather would in fact impact, if I'm selling ice cream, certainly the temperature of the day I would expect might influence the demands, right? And I would have a good idea what the temperature of the day is going to be. And so that could be a covariate there. You could also, and I'll talk if I have time at the end of the thing, mostly I'm going to be talking about sort of a static model, a two-stage model, but we're also looking at multi-stage extensions, where in that case, you could think of the covariate as being, if you have a time series model of things happening over time, then you could think of the most recent observation of the bands as being a covariate, because that is kind of what you would use to predict the future in a time series model. And so that's another kind of example.
Okay, so I guess this covariate is like something that you assume in the model, that you have a particular type of covariate, or? It's really anything. I mean, it's thinking of just, in general, I have this uncertain quantity, this parameter that I'm trying to predict. And that's kind of the whole, question of machine learning is, how do you predict things based on some other information that you have? And so this is sort of just a flexible framework. So if I have some other information that I would be using to predict this uncertain quantity, how do you fit that into this optimization question? Right, thanks.
Okay, if there's no more questions, I'll then sort of start talking about some of the general approaches people have thought about this, and sort of see what I talk about. And so, this idea of this integrated learning and optimization, is not people that have been, think this, especially more prominent. And so one of the things I think is where, you have these two paths, right? And it separately is clear that you might miss something, right? So some looking at is of maybe we should modify the learning step, where essentially change the way you do the learning, where instead of just trying to predict accurately the value y, you think more actually, how is the prediction going to be used downstream? If you sort of look at the fact that it's going to be used in an optimization model, your goal is to make a prediction of y that would lead to good decisions, right? So you factor that in. And what the way that translates into this, changing of the first step in that learning and optimization two-step process is you change essentially the loss function in the machine learning model to sort of reflect the fact that you're going to use it in optimization later. Okay, so it makes it kind of this rather complicated loss function, and it turns out that it ends up being a rather challenging training problem to solve. But if you could solve it, you could expect that you'll sort of improve your decisions, and that's kind of the goal there. Now, one thing that's maybe a disadvantage of this is it's not modular, right? So in the sense of here, you're really sort of re-engineering the machine learning with that optimization after the fact. And so if I want to have a new machine learning prediction model, then I have to kind of again re-engineer that with the optimization in there. So every time you want to make a change to the prediction step, you also have to sort of factor in the optimization downstream. So it sort of loses that modularity advantage. So the second approach, and that's going to be, the work I'm going to present today is going to fit into that, would be to leave the prediction model the same. So it's going to be modular, but you would to change the optimization step. Okay, so the idea is to change that optimization model to reflect the uncertainty in the prediction. And these are some references, and I'll talk more about these in more detail, because they closely relate to the work that I'm talking about today. And then just to mention, I'm not really going to talk much about this, but just, as an overview of the different ways you might approach this problem. Another approach, which would be, I think, the best one if you could do it, but it just seems really, really hard, is essentially direct solution learning, right? So the ideal thing would be to say, okay, if, X is the covariate that I observed today, and ultimately I want to make a decision Z, right? I would really ideally just want to have a mapping that says, given X, tell me what is Z, right? And try to learn an optimal such mapping. And so there is some work, I just want to point out, some of this overlaps with this approach too, where people have also looked at trying to do that. But this just in general, I think is a more challenging goal in the sense that it's hard to create this mapping so that you'll satisfy constraints. If you have sort of hard to satisfy constraints in your model on on the decision Z, and it just really does feel really restrictive in terms of dimensionality. It seems hard to believe that we could do this with larger dimensions of X or Z. But it is sort of, would be the ideal. Okay, so I'm going to move on now to discussing the approach that we analyze. And again, it fits in that second approach of changing the optimization model. And so here, the setup here is we have these observed observations. Okay, so yi are the parameters of interest that show up in our optimization model, and the xi's are the covariates. And we assume that these things are drawn from these random variables y and x, which obviously are correlated because that's why we would expect that we will learn something from y by observing x. Now, we don't necessarily always assume that these observations are independent of each other, I from 1 to n, although that's certainly one way to meet the assumptions that we would need in the theory that we have. But you can have other cases where these have some correlation if some other assumptions are satisfied. And so the setup is then, we're going to get a new observation of this random variable x. So let's call that one little x. And so now we essentially have this kind of conditional optimization problem. Okay, so given that we've observed this little x, now we want to minimize the expected cost of this c given our decision z and the conditional distribution of the random vector y given this observation. Okay, so here's the approach that we're going to study, and we're naming it this empirical residuals sample average approximation. And so the first thing we're going to do is we're going to make an assumption. Okay, so this certainly is a restriction in terms of the theory that we'll be able to prove. The theory will only be valid under this assumption, but we'll also see, we'll do tests, to sort of show that outside of this assumption, the approach still can empirically potentially be useful. But the assumption is that we have there's a model, okay, underlying this, where the output y is given by some function unknown to us, f star of x, plus some random error epsilon. Okay, so that which would have 0 mean. And in particular, this is a key limitation in this assumption is that this error is independent of the x itself. Okay, so that's something that we need in our analysis, and certainly provide some limitation in the results that we get. But under this assumption, then basically what we can kind of rewrite this conditional expectation problem where we just plug in this f star of x plus epsilon into the objective for the y. And now we're sort of minimizing the expected value. So we just plug in the little x that's observed, and then we just have this random variable epsilon. So that's the thing that we still have to handle in this. And we'll also assume that we have a function class f, such that f star is in this, and that's going to be what we would sort of train over. So that if we have this function class correct, then our prediction model would eventually converge to f star with enough data. And so that's another assumption there. Okay, so here's the approach. Okay, and so this approach, as is one that we are going to analyze. But it turns out that the basic idea has appeared in at least these 2 other works that we're aware of. And so San and Deng sort of proposed this with a particular setting of a particular prediction model. They were just using ordinary least squares. And then this other paper, they looked at sort of a similar approach here in a specific application. Okay, so they were sort of doing this in some specific settings, but they have the same general idea. And so the idea is in fact, I think, pretty simple. I mean, it's a lot to wrap your head around kind of the framework of this model, but doing this seems kind of straightforward. So the idea is it's still a 2-step process. So in the first step, you can use your favorite machine learning prediction model to estimate that function f star that's unknown to you. And we'll call that estimate f hat n. Okay, so that's kind of the output of the prediction step. The sub n indicates that, of course, that depends on the sample of data that you have that you used to build that. But the other thing that we're going to ask for an output from step 1, which you can always get from any prediction model, is what we'll call the empirical residuals. Okay, so this is just the errors that come from that fit model. Okay, so yi are the actual outcomes that went with xi, and so this residual is just the yi minus what the model predicted, that trained model, at that point xi for each of the points I. Okay, so we have these n kind of residuals that come out of this prediction model, and we ask for that as well from the prediction step, and of course that you could always compute if you have f hat n in the data. And so then the idea is to basically, again, kind of do a sample average approximation. But now what we're going to do is we're going to build the samples of the sample average approximation based on the point prediction f hat n, and just plugging in these residuals directly that we got from that first step, from the training step. Okay, so we just treat those as the samples. And so it really is like a sample average approximation problem, so that's why we give it that name. But it's coming from these empirical residuals. Okay, so we solve that model, and we get a solution out of that, which we call z hat n. It depends on x, because x had to be plugged in to this f hat to get your point estimate. And so that's the decision that this method outputs. And so, again, this is nice and modular, like that traditional approach. So easily you could, if you want to have a fancy neural network model to do your predictions, you can do that. Once you've done the training, however you do it, just have to compute these residuals, and then you can plug this into step 2. And so the thing that we found surprising, given that this, to me, it just seems like, oh yeah, this is the thing, such a natural thing to do. We couldn't find a general convergence analysis. And so this paper Ban et al., they did some convergence analysis for that specific application. And Sen and Dang, they didn't exactly do sort of the type of convergence analysis. They more looked at convergence of a specific stochastic approximation algorithm. They didn't look at sort of the convergence in terms of the errors from the data sampling and things like that. And so that's something that we worked at. Is we wanted to just establish, does this really converge? Is this a reasonable approach? And ideally also, can we bound the convergence rates? Okay, so that's kind of the main theoretical contributions here. And then also, the other sort of risk of this approach is if the sample size, the convergence, of course, is going to be in the limit, or maybe some things there. But if the sample size is small, maybe you're not going to get such good solutions out of this approach. And so, are there any things that we can do that might sort of improve the solutions you get, at least empirically, when the sample size is small? So we have a couple ideas along those lines that are new as well. And so the first thing I'll say is one of those variants. Okay, so in terms of something that we might hope might work better with the smaller sample size. And one of the risks is with the small sample size is you can get some overfitting, right? Because this f hat might really be overfit, and these residuals might not be really a good estimate of the residuals for putting into the stochastic optimization model. And so we actually took some inspiration from Jackknife methods. And we had this idea that we could do a separate estimation doing sort of a leave one out analysis, right? So for each data point I, you do the prediction model using all the remaining n-1 data points. And so you get this f hat, say, negative I, that's sort of representing the model that you would train having left out one data point. And then for each data point, when you do these residuals, you do that based on, for the I observation yi, I do the residual calculation using the version of the model where I left that one out. So that sort of kind of removes a little bit of the, I think, bias that might be introduced in the calculation of these residuals. And then we would use these residuals, added to either f hat n itself or maybe the leave one out estimator. So that's two variants. I'm not going to focus on just the one where we use still the f hat n. Which we call Jackknife, but there's another variant we talk about where you'd actually use the leave one out point estimate as well. And so it just basically changes the samples you use, but otherwise it's the same structure. This is still sort of a sample average approximation model that we propose to solve. It's just sort of a different way of generating the samples based on the data that was output from the prediction step. The other, of course, important difference is this is a lot more work. In the prediction step, you have to do sort of a separate prediction step with every data point left out. So there's a lot more work in the prediction step, but it's roughly the same amount of work in the optimization step. Okay, so before I start talking about sort of the theory results that we have, I just want to sort of highlight kind of what we see as like the main alternative approach for this problem setting, which is known as this non-parametric reweighting that was proposed by Bertimus and Callis. And the idea that they have is they solve a problem that really looks exactly like the traditional sample average approximation, where the data points, the samples that you're using are yi. Okay, so those are exactly the historical observations that you have of the uncertain parameters. But what they do is they change the weighting. So instead of it being 1 over n, having them all equally likely, as in sort of traditional sample average approximation, they have this way of sort of saying, well, we should reweight to them based on the current covariate x. Okay, so that's this Wn of I is sort of this weight function, which is something that they want to learn. Okay, so they want to use train these Wn functions based on the observed past data. And so, they have different variations, but basically, the general idea is that this weight should be putting, more weight on observations for which the xi is close to the x, right? So you have a new x. If this new x is close to a past data point xi, then that should have more weight because you would expect that to be, closer to the output yi that you have. And so they have a number of variants of that. The advantage of this is, it's sort of non-parametric. And so they really actually require minimal assumptions on the historical data and on the form of the function, f star, in the prediction step, in order to obtain asymptotic convergence. Okay, so they have a pretty general set of assumptions for which you can show that this method does converge to an optimal solution when you have, as the data increases. But the drawback is that this can be quite data intensive, in particular when the dimension of the covariate vector x is high, potentially also when the dimension of the parameter vector y is large. And so it certainly has very nice asymptotic theory, but we're a little bit motivated on seeing, well, what happens for if you don't have such a huge amount of data, could you potentially do better? And we'll see some empirical comparisons to this a bit later. Okay, so I'm certainly not going to have time to talk about proofs, but I just want to give you a flavor of the types of results that we're able to establish about this approach. And so we're going to let v star of x be the optimal solution of the problem. Remember, it was conditioned on this new observation of the covariate x, so all this depends on that covariate x. And we'll let f kappa of x be the set of kappa optimal solutions of that true problem given the covariate x. And so the first thing we would really like to have is just this asymptotic result that would say, the cost of the data-driven solutions will approach the minimum costs of the true problem as you have more sample sizes. And so this is a convergence in probability as the number of data points that you have goes to infinity. That's what this notation is. And so what you'd like to say is that, if I plug in the solution that I get from this procedure, that z hat n of x, and I take the expectation again over this cost, using the true thing f star, right, which you don't know, but that's the thing we would like to have, but that would converge to the true optimal solution. So that's asymptotic optimality. That's one result that we like. And so just to kind of give a flavor of this, I just want to sort of say the types of assumptions that you need. And so, for example, in this setting of this two-stage stochastic linear programming, so exactly the setting that we had in this resource allocation model, but a little more general as a general two-stage stochastic linear program. Then, the types of assumptions you need would be, okay, this is an assumption on the optimization model, so this will satisfy the assumptions we need for the optimization side. But then for the prediction side, we basically just need point-wise consistency. So for every x, this model does convergent probability to the true f star, as n goes to infinity. And then also we need something of a mean squared error consistency. So it's sort of another condition, a little stronger condition on the prediction training procedure. And assuming you have both of these conditions, then you can show indeed what we want, that these solutions z hat n are asymptotically optimal for any, almost every new observation, covariate observation X that you would see. We also can have some similar consistency results for these Jackknife estimators, the Jackknife solution. So that's where we did this leave one out analysis and built the samples based on that. And there we just need slightly different assumptions on the regression procedure. So we still need point-wise consistency, so that assumption isn't changed. But now for this mean squared error consistency version, we need that to hold for the leave one out one. Okay, so this is a slightly different assumption. There are cases that satisfy that, but there are also cases that do not satisfy that, but do satisfy the first one. So just to be aware that this is a potentially slightly stronger assumption for this to hold. But under this assumption, again, that turns out to be what's needed to have this asymptotic optimality result. And then finally, to sort of talk a little bit about some flavor of some of the results that we have in terms of rates of convergence for these solutions. And so here we need to say something about the rate of convergence of the prediction step. And so the assumption here is there's some constant alpha such that this regression procedure satisfies a certain rate of convergence in terms of both the pointwise error and the mean squared estimation error. And so we have these assumptions. So this is written in this sort of n to the negative alpha kind of generic term alpha here. So for things like ordinary least squares or lasso, these things are satisfied nicely with alpha equals 1. But for some of the more non-parametric prediction models, these things might depend on the dimension of the covariate vector X in a not nice way. But at least they're more general model classes, so they can be expected to converge on more general model classes. And so under these assumptions, again, stating this informally, leaving out all the details, but basically we can establish that the error or the expected cost of the solution that we get out of this is on the order of the optimal cost plus this term here, which is growing on n to the negative alpha over 2. So if in this nice case, when you're in this kind of more restricted model class setting, like least squares or lasso, you get to alpha equals 1. That's kind of like the Monte Carlo estimation rate that we're used to. If you use a non-parametric model, so that's the advantages, then you're much less restricted than the function class that you're estimating. But you get this not so nice dependence on the dimension of the covariate vector. So we sort of can see that from our analysis. And then we have also some finite sample guarantees. And so this is sort of estimating the probability that the set of solutions that you get from this thing are near optimal to the true model. And so here, this kappa greater than 0, that's an optimality gap. This delta is going to be kind of a reliability level. And we want to say, well, can we bound the sample size required such that the set of optimal solutions to this empirical residuals problem is certainly going to be within the set of optimal solutions or kappa optimal solutions to the true problem with some high probability. Okay, so that's the kind of statement you would like. And then the question is how many samples do you need to be assured of that? And so you can get bounds on this in different settings depending on the form of the function f and the prediction model that you have. So for example, if we have least squares regression, then this is roughly the estimate that you get. And just highlighting here, so the kappa, the optimality shows up there, and 1 over kappa squared is the dominating term there. So that's sort of kind of the Monte Carlo error estimate that you would expect. So that's there. In terms of the dependence on the dimensions of the covariate vector, the parameter vector, and the decision vector, it's sort of linear in the decision vector. So that's kind of, again, what you would expect from sample average approximation results. Now we have also a linear dependence on the parameter vector. So that's something new that's coming from a prediction step, but it's hopefully not too bad. But then we have this product of the covariate with the parameter vector. That's something that sort of props up from the joint thing that's happening here. And it's maybe not the best, but that's what we've been able to show. But what we can see is if we would know, for example, F star is S sparse, right? So then the lasso theory gives us better prediction if this really is a sparse model. Then you can improve things. So where we had a dimension of X, we replace that with S times the dimension of X, right, using this S sparsity. So that improves a bit the analysis. And so it sort of shows that the procedure that we have, the analysis we have, is able to adapt to improved analyses of the prediction models when you have that. But then to sort of show, the other case, and there's a whole bunch here, but this is assuming a much more general model class, so just F star is Lipschitz, and you're using some sort of non-parametric regression, for example, in this case, k nearest neighbors. Then, okay, don't need to look at all the details here. Much of it is similar to what we saw before, but I just want to point out the bad part here is we have this now exponential dependence on the dimension of the covariate vector X. Okay, so that's the kind of the price you pay for having a much broader function class in the prediction step. Okay, so good. So then I want to sort of show now a little bit of how this works empirically. And so we're going to go back to that resource allocation model that I introduced here. So it's a two-stage stochastic linear program model. We're going to look at a case where we have 30 customers and 20 resources. And we're going to assume that we're going to assume a known model. Okay, so for the purpose of this experiment, we're going to assume that we know this model, where the demands are given by this function of the covariates X, where the demands actually only depend on 3 covariates. Okay, so it's sort of a sparse model. There's these coefficients beta star, there's these sort of centers alpha star, and then there's some errors that are zero mean normal errors. But the key thing I want to point out here is we're going to do kind of 3 cases here where these X's, the covariates, are raised to different powers. Okay, so the case where least squares or lasso matches the model class is when p equals 1, right? Then it really is a linear model, exactly what OLS and lasso assume. But we also want to test cases where there's a mismatch. Okay, when p is 1/2 or p is 2, then the model class that we're going to train, we're still going to train either ordinary least squares or lasso as the model class, but there will be a mismatch. Okay, and that's kind of something we want to see. Okay, well, if we don't have the right model class assumed, could this still be useful? So we're going to analyze that as well. And then we're going to have, we'll report results for 2 different cases for the dimension of the covariates, 10 or 100. And by the way, so the dimension of the covariates is 10 or 100, but the true model only uses 3 of them. Okay, so we just have a bunch of extra ones there, for the purpose of kind of maybe distracting the prediction model. Okay, and then we're going to estimate, what we're going to do is we're going to sort of have our method that produces a solution. We're going to repeat this many different times in many different data samples and many different covariates X. So each of those gives us a sample of the cost using this method, and we're going to sort of compare that to the true optimal cost because we really do know the underlying model. Okay, so we're going to, for each output, we're going to have the expected cost from the solution that we got, and the expected true cost, which we can calculate because we know the true underlying model in this case, and we're going to calculate the optimality gap. And then we repeat this many times, and we're going to then have a range of different optimality gaps, and we're going to display that with kind of bar whisker plots. Okay, so here's that first set of results. And so our the method we want to compare is using this empirical residuals approach with ordinary least squares. So in this case, we're not taking advantage of the fact that the underlying model is sparse, we're just training a linear model anyway. And then we're going to compare this to using that reweighted SAA approach of Berthinus and Callis, which again has a very nice asymptotic theory. It sort of converges in the limit for a very broad range of models, but that's asymptotic, right? So we're interested in maybe in smaller sample sizes, how does this perform? And so on this plot here, we're going to see, this is for dimension of the covariance is 10, and here's dimension of covariance is 100. And on what we're varying at the x-axis here is the different sample sizes. So from small sample size relative to dimension to something quite large relative to dimension. And so the black boxes and whiskers here are from the reweighted SAA, and the red is from the empirical residuals. And then what these represent here is the line in the middle is the median. The box is the 25 and 75 percentile of the outputs from all these different runs that we ran. And then the edges of the whiskers are the 2 and 98 percentiles. Okay, and we'll see, you notice even that the upper ones we sometimes truncate because those can go too far and we want to be able to zoom in on the boxes a bit. And so what you can see for both dimension 10 and dimension 100 is that while certainly the reweighted SAE approach is converging, it's going down as you would expect, roughly, the convergence is very slow. Okay, so with 100 dimensions on the covariates, even at 10,000 data points, the optimality gap is ranging, you know, around 5% still. Whereas with the empirical residuals approach, we were, you know, significantly below 5% already at 200 as the data points, and getting, you know, very close to apparently optimal beyond that. Okay, similar results for the 10 dimensions. So let's look now at the misspecified model classes. So we have on the top row here is when p equals 0.5 and the bottom was p equals 2. And notice in particular, first of all, the y-axes are different. So for whatever reason, when p equals 0.5, that model mismatch isn't so bad for this empirical residuals. We still have errors that are going down. Maybe not going all the way to 0, but they got down to something pretty small. And certainly they're less than with the k-nearest neighbors approach again. And so somehow this, even though they're mismatched there, it's not so bad. But when p equals 2, things get worse, right? So somehow the model mismatch hurts us more. We start off higher, but we seem to sort of convert to something that's, you know, not close to 0. It can be expected because there's the model mismatch. But still, for, you know, any of these finite sample sizes, the approach still seems to be doing better than the reweighting SAA approach. Okay, so that's what we found with that. So the next thing I want to show is this Jackknife thing that I briefly mentioned, which is this different way of generating the samples, which we hope that might do a little bit better than the basic empirical residuals approach when the data is small. And so that's going to be just comparing those two things. So we have the empirical residuals approach with ordinary least squares, and then the Jackknife, again, with ordinary least squares as the prediction step. And we do sort of find that, and in particular for the case when the dimension of the covariance is larger and the data sample is quite a bit smaller, using that Jackknife approach to generate the scenarios for the smaller data, you know, is seeming to do quite a bit better. Of course, as the data gets larger, they both are converging, and so the difference kind of goes away for larger data, as you might expect. Okay, and the last thing I just want to mention is that you know, kind of again highlighting the benefit of this approach being modular, right? So suppose I using ordinary least squares, that might have been what I was doing 20 years ago, but now we figured out, oh hey, lasso, you know, it does really well, and oh, actually we think there's good reason to believe our model is sparse, so we start using lasso in the prediction step, and we find that in fact that helps a lot. Okay, so at least for the larger demand. So when the dimension of the covariate vector is small relative to the true sparsity was 3 in the underlying model, lasso doesn't have much benefit because, you know, it's not that sparse, 3 versus 10. But when it's 3 versus 100, that's, you know, a very sparse model. Then we see that using the lasso, which is the blue line, is much better than using the ordinary least squares. Even though ordinary least squares is the correct model class, it's still linear. So for a large data set, that's okay. But again, for smaller data, the fact that we were able to use a better prediction model really translated to better solutions in this approach. Okay, I think, you know, we had similar results for the misspecified model. I think I'm getting close out of time, so I want to just wrap up. And in fact, you know, I was going to talk about extensions, but I'll just very briefly mention each of them. So the first one being that instead of solving in this empirical residuals model, we created these samples, and then you just solve that sample average problem with those samples created in that different way. A very natural thing you might consider doing is changing that model even further and doing kind of something distributionally robust around those samples. Okay, so if that's an optimization area that you're familiar with, you might have already been asking, oh, why don't you do that? And it's certainly something we thought about and we're working on. We've developed some of the theory related to that. So that's again something that I wouldn't expect to be a great benefit if the sample size is large, because then, regular sample average should be working pretty well. But for smaller data sets, this could help lead to better solutions. And then we've also looked at extending this to multi-stage models, and I won't have time to even describe the framework there, but certainly in multi-stage settings, this is something we've thought about, and we have some ideas how you can do this. And it turns out that it fits nicely into some of the algorithms that are known for solving multi-stage stochastic linear programs, in particular the stochastic dual dynamic programming. You can plug that in and you have an algorithm to solve it as well. So with that, I'll stop with some, just concluding remarks here. And so, the nice thing about this approach is, again, I think it's modular. It's a way to include this covariate information in optimization, but still keep those prediction and optimization models sort of separate. And so one of the references that did it the other way, where they changed the prediction model, was a paper by Grigas and Al-Maktoub, which they have a really nice name for it. They call it Smart, Predict, and Optimize. So the two-step approach, predict and optimize, and they call it Smart, Predict, and Optimize. And it's really an interesting paper and a really nice approach. What I would say, this approach is more like doing it differently, where they predict, then smart optimize. So be smarter in the optimize step instead of being smarter in the prediction step. And so we showed that, this convergence, we sort of derived various assumptions and conditions to show what converges and estimate the rates. And then, there's this key trade-off here in terms of choosing the prediction model class, right? So on the one hand, you'd like to have a general model class, so that you can predict anything. But on the other hand, even using a misspecified model, with limited data, that might actually be better because you can predict better that misspecified model with limited data. And that's kind of some of the, related to the results that we saw there. Okay, so in terms of future work, I mentioned the distributionally robust and multi-stage extensions here. I mentioned at the very beginning, we have this assumption that the error, the underlying prediction model, the error is independent of the covariate X. That's sort of a restrictive assumption. We'd like to see if you could partially remove that. And then in terms of the convergence rates or the bounds on the sample size, these were only upper bounds. These were bounds that what our results are just saying, if you have this big enough sample size, this is, then you're within a certain error. We don't have any matching lower bounds, and I don't even have a guess whether our current results are tight. And so that's certainly an open question. It's established lower bounds, so if these results are tight. So with that, I'll stop and happy to take questions.
Thank you, Jim. Please interject if you have a question for Jim at this time.
I have one question. In terms of actually solving this problem, you can pretty much use whatever you had for solving the SAA problem. Is that correct, or is there anything?
Yes, right. Yes. There's nothing about this analysis that depends on the algorithm for solving the optimization model. It's really just it analyzes the solutions out of it.
Okay. And in terms of, I guess, sample size, I mean, it was a bit harder to sort of get an idea if, I mean, to get some, let's say, within some confidence interval of the optimal for SAA, how does that compare to the bounds that you get? Is it much larger? I mean,
yeah, good question.
An idea.
So I mean, even I can answer that a little bit by giving a flavor of the analysis, and the analysis, in a certain sense, I mean, it's kind of the natural thing you would do is say, well, what sample size do you need in order to get the prediction model accurate? And then once that's accurate, what sample size do you need to get the sample average stochastic optimization accurate? And just kind of put those analyses together. And so that's how it works. And so in this sample size, so this is assuming you have a linear prediction model and using least squares regression, and this is that traditional two-stage stochastic linear programming setup. So bounds that you get, this part of the bound, the part, depending on the kappa squared and the dimension on the decision variables, that's all exactly what you get from the optimization analysis, the traditional sample average approximation analysis. And it's these parts here that depend on the dimension of the covariates and the dimension of the parameters y. That's the part that's coming from the prediction side. And so this is what you pay for the fact that you have to predict. And so you kind of just put them together roughly. And then, you see that if you use the last way, if you had a better prediction, you can get some improvements. Instead of having the dimension of x, you get the sparsity times the log of the dimension of x as an improvement there. So that's how you could see how that improved prediction translates to improved sample size estimate. But this part here, this is the part that's that's for the optimization side. That's the same. And that I should say that's a function of our analysis. We just kind of did these separate and took the existing results and put them together. I'm oversimplifying that. I mean, there's a lot to kind of do that correctly. But that's the approach. And this is why I raised the question of, I don't know that it's tight. I mean, maybe some of these things aren't needed. Maybe this is the bound, but maybe this isn't the best you can do.
Okay, thanks.
Other questions? If not, let's thank Jim again for a nice talk.
Thank you, everybody. I'll stop sharing.